In this video, we're going to start talking about graphical models or probabilistic graphical models. Specifically, we're going to talk about Bayesian networks, which is a type of graphical model. So we're going to talk about the general idea behind graphical models. I'll define what a Bayesian network is, and then we'll look at examples of graphical models that we've already seen so far. So we'll look at how naive Bayes and logistic regression can be viewed as Bayes nets. And then we'll talk about how to do inference in Bayes nets. So a probabilistic graphical model is a way of representing a probability distribution in a way that the distribution can be represented, can be encoded such that we can read off conditional independence structure from a graph. Okay, and I'll explain how that works, but the idea is we want to encode, what variables are independent of other variables given other variables, based on, or encode that in a graph so that we can use graph algorithms to do inference and learning. And this is all just about how we abstract the idea of conditional independence, which is a very statistical idea, which is probabilistic, and abstract it in a way so that we can use computer science to think about how to efficiently reason about probabilities. So here's an example. This is a Bayesian network that describes a conditional independence structure. And what makes it a Bayesian network is that it's the distribution is represented by a bunch of variables, which are the nodes in the graph, the nodes in the network, and edges between the variables, or directed edges between the variables, so they have arrows attached to them, they have a directionality that describe the conditional dependencies. So there's a conditional independence structure here, and again, what we're trying to describe is a full joint probability distribution. So we're looking for the full joint probability distribution of P of L, R, and W. So winning the lottery, raining, and the ground being wet. And what this Bayesian network structure tells us is that this joint probability actually factorizes into this form. So specifically, that win lottery, because it's sitting by itself in the graph and it has no connections to any other nodes, it is completely independent of everything else. And the variable for whether it's raining is dependent on or is related to whether the ground is wet, right? And this example is obviously a cartoon yet understandable situation, right? Winning the lottery has nothing to do with the weather, but whether the ground is wet certainly depends on the weather. And the idea here is that there's some probability of there being rain, and then there's some probability of the ground being wet given the rain. So we can continue this. We can grow this model by including other variables. And here we might have another variable where if the ground is wet, we might expect there's some probability of us slipping, in which case we would have a conditional probability factorization of the joint. Okay, so we have the full joint probability, and we can factorize that into a bunch of prior probabilities and conditional probabilities. And we can see that we again have the same structure that we had before. So we have P of L by itself, then P of R by itself, sort of, but then there's a P of W that depends on R, and then P of S that depends on W. And one of the interesting things here is that this whole Bayesian network structure shows us that we can ignore certain ideas, right? We could have written this easily as the P of S given W and R, right? Because in some ways R determines which conditional probability distribution we use for W, and W then determines what distribution we use for S. But if we already know the value of W, we don't need to consider R anymore, so we can cross that out. So to summarize, this I guess definition by example, a Bayesian network describes a probability distribution among all variables by putting edges between the variable nodes, where the edges represent us having a conditional probability factor in our factorized probability distribution. And it's important to note that by the structure that we've of the factorization that the network implies, restricts that structure will restrict the different possibilities of what distributions we can have, fit that factorization. So you can't actually express all possible distributions, all possible joint distributions, if you're restricted to these factorizations. So a few interesting things happen when you look at these factorizations. So consider this new network, which is, I guess, a slight variant of what we had previously, where now we have another possibility for why the ground may be wet. So the probability distribution, or the factorized probability distribution corresponding to this Bayesian network, is the following. So now we have the probability of R by itself, we have the probability of C by itself, C being the car wash, so it's either going to rain or it's going to be a car wash, and then we have the probability now of wet ground given car wash or rain, or not. It's not really an or, car wash and rain, right? The two variables considered together. And these variables, remember, they can take multiple states, right? This is just the conditional probability table that's indexed by the state of C and R. So we're not saying that C and R are both true. We're saying that whether they're true, 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 false, false, true, or false, false determines the probability of W. And another way to characterize how a Bayesian network translates into a factorization of a joint probability is that we say in general that the probability of X is going to be conditioned on the parents of X. So where X here is wet ground, right? We look at, what are the parents of X? And parents in the sense of the graph theoretic sense, where these are the nodes that have directed edges coming into this variable. So we have, wet ground is our node. So what are the parents of wet ground? Well, rain and car wash are the parents. So these are the variables that determine which conditional probability we're going to use. And you can do the same thing with slip. So slip, the only parent of slip is wet ground. And you can do the same thing with rain and car wash, who have no parents. So therefore they just have, P of R and P of C. So you can probably start to imagine how this type of organization enables more efficient inference of, figuring out different conditional probabilities you might be interested in deriving from the full joint probability. And but before we get into that, let's look at some examples of other distributions we've looked at and see how they can be viewed as Bayesian networks. So here are two Bayesian networks, and I want you to just think about, what do these look like? So, what is the joint probability of the top one? So again, for each node, we look at which variables are its parents, and we say we're going to have a probability factor that is the node conditioned on its parents. And in this case, each of the nodes, or each of the X nodes, X1 through X5, has Y as its parent, right? Only one parent. And that means that we have the probability distribution of, it's going to contain all these terms that have to do with the probability of X given Y. So that should seem a little familiar. And then on the bottom, we have the opposite. We have now X's are, the arrows are coming out of the X's toward the Y, which means that the X's have no parents, but the Y's, or each Y has all of the X's as its parents. So these are the distributions corresponding to these Bayesian networks. And you can see that these should look familiar. So at the top, we have the naive Bayes factorized distribution, right? It's essentially the conditional independence assumption about the features given the labels. And then on the bottom, we have something that looks kind of like logistic regression. It's not exactly the same thing because we actually have the input likelihood here, right? We have P of X. But if you divide out P of X, then you end up with P of Y given X, where X is the full input. It's all of the dimensions of the input. So if we think about it now, especially for the case of naive Bayes, we know that we were able to compute things pretty efficiently with naive Bayes, right? We didn't have to worry about some gigantic probability table that considers, if there's D dimensions, we have K to the D possible probabilities for y, right? That would be the worst case scenario if we had to consider a p of y given x for an arbitrary joint distribution. Right? It really simplified to the point where we just needed to add up all these log likelihoods for each dimension. And that's really an instance of the power of Bayesian networks, but where Bayesian networks generalize beyond naive Bayes. And on the bottom, we actually have the opposite effect, where if we were to implement this, in the most general way, the probability table of p of y given x1, x2, x3, x4, x5 would be huge. Right? Again, this is exactly what I just described. We would have to consider, k to the 5 different possibilities for p of y given whatever the states are of x1 through x5. And what we did instead was we parameterized this, right? We didn't consider all possible probabilities. We just considered the probabilities that would come out of a logistic squashing of, a linear combination of the x variables. And that's a big restriction, right? In general, that quickly or strongly restricts the space of possible distributions we might be interested in representing. So from these examples, you should be able to see that naive Bayes has in some sense a nice, in quotes, probability distribution in terms of efficiency, and then the downstairs thing, which we've shown we can parameterize to make logistic regression, but in general, the probability distribution that's described in the bottom is not nice, right? In the sense that it's expensive to think about the bottom distribution. So then looking at the graphs, what is it about the top graph versus the bottom graph that make them more or less efficient or more or less expensive to reason about? And that gets us to the idea of independence. And what the naive Bayes graph really takes advantage of is this conditional independence, which was the fundamental assumption. It was the first thing we talked about that enabled it to be inexpensive to work with. And in a Bayes net, in a general Bayes net, that's not necessarily just this one layered thing like the naive Bayes graph. In general, the idea in independence is that each variable is conditionally independent of its non-descendants given its parents, which is kind of a lot to think about. So let's look at some examples. So consider this Bayesian network on the right, and let's look at the variable c. So variable c has a parent a, and let's say we observe a. So at this point, what variables are independent of c? Now we know E depends on C because E is C's descendant, or more specifically, it's its child. But according to the rule that on the left, B and D are independent of C. And you can write out the probability distribution described by this Bayesian network and work this out and see why it's true. But then furthermore, you can do things like considering the variable E, and suppose we observe the parents C and D. So we know the value of the variables C and D, and we want to consider, is the variable E dependent on any of the other variables on top? And the answer is no, because according to the rule, again, C and D are the parents, and E has no non-descendants. So E becomes independent of A and B. And again, you can work out the math to see why this is the case if you just write out what the probability distribution is described by this network. And another rule for independence in Bayesian networks is that each variable is conditionally independent of any other variable given its Markov blanket, which is a new term here. Most of you probably have not heard about it, but a Markov blanket is the set of all parents, children, and children's parents of a node. So in a family tree nomenclature, that would be something like the parents, the children, which are easy, and then the children's parents, kind of have a weird interpretation, but you can think of it as like spouses or co-guardians of the children. So in this case, here's an example. So node C has a Markov blanket that includes A, E, and D. So A is a parent, E is a child, and then D is a child's parent. So if this were a family tree, that might be the C and D might be spouses or co-guardians of E, but the analogy breaks apart a little bit. but the idea is that if you ever observe all of the members of the Markov blanket, then that variable becomes completely independent of every other variable in the network, and that makes things a lot easier and a lot more efficient to reason about. So let's think about how we can use this independence, especially in the task of inference. So given a Bayesian network, describing a joint distribution of x, y, and z, one question we might ask that's a problem of inference is, what is p of y? Right? What is the marginal probability of one variable, which would essentially require us to enumerate or sum over all of the possible settings of x and z, all the remaining variables. And the first approach is enumeration. So let's look at what that would look like. So if we have the same distribution we looked at before, this was the rain, wet, slip, and a car wash example. We had this structure, this Bayesian structure. So it was P of R and P of C had no parents. P of W had C and R as parents, or W had C and R as parents, and S had W as a parent. And let's say we're trying to figure out the probability of R given S. So we're trying to figure out the probability that it's raining given that we slipped. Right? So we walked down the street and we slipped on the ground, and now we're wondering, is it raining? Now it's kind of a silly question, but you can imagine this could happen to a robot. So a robot is rolling down some street on some mystery planet that it's exploring, and it slips, and it doesn't have weather sensors. So now it's trying to figure out, based on its locomotion sensors, whether it's raining. And the way we would do that, the way we would write that out, is we would want to divide or sum up the joint probability of all the variables for all the possible settings of W and C, or those are the variables we don't care about. And then we'd want to divide out the probability of S. But for the dividing out, let's just say we could normalize that out. And so we would just say that it's proportional to summing out all of the variables that are not involved in our target distribution, right? We're looking for P of R given S, so we want to sum out all the other variables, which is C and W. And here I've written the factorized form of the joint distribution, but in general, this is just the idea that we want to sum out the joint distribution, the joint probability. And this is expensive, right? Doing it the way that's written out is expensive because we have to enumerate over all the possible settings of W and C, and that's bad already in this example. But in general, that's essentially like O of n variables for which you have to consider the joint setting of. So that's like k to the O of n, which is really huge. So we want to think about how we can use the Bayesian network structure to alleviate this problem. And it's not so much the structure. I mean, you can see it right on the screen. It's right there in algebra for this example. But in general, when we have these Bayesian networks as inputs, we're going to be dealing with distributions that are a lot harder for a human to see how to simplify. But let's try to simplify this case. So we have a sum over W and a sum over C. And what essentially the trick that we're going to try to do is we're going to try to pull out terms that are not affected by the variable being summed over. So for example, P of R is not affected by either W or C, so it gets pulled all the way out to the top. P of S given W is not affected by C, so that gets pulled out of the C summation. And then that's as far as we can get. So then now we're down to a slightly simplified form, but it's still pretty expensive, because if you look at this, we're eventually going to sum over this distribution P of W given C R, which is a case where we have to look up a probability distribution over two variables. And in general, if you have if you have n binary variables that are in the conditional, you need 2 to the n different probability distributions that you need to be able to look up. So that's expensive. We want to try to avoid this, but for now, this is how you do enumeration. And you can view this as a tree. Sometimes it's helpful to think of it that way. So we want to consider all the possible settings of W and C. And because these are binary variables that are either true or false, we can draw it out nicely as a tree. So we have P of R that's sort of by itself, and then we have to sum up over all possibilities of this, second subtree of P of S given not W and P of S given W. So on the left is not W, on the right is W. And then down at the next level, we want to then sum over all the possibilities of C, right? Not C or C. And so maybe this is a useful way of breaking this down. But overall, the idea of enumeration is the wrong idea because it's not fully taking advantage of the independence here. But it's useful to think about because it's the goal that we're going to try to accomplish, but we're going to do it in a more efficient way. So instead, what we're going to look at is the technique of variable elimination, and it looks at the beginning it looks almost the same as enumeration. So we have this summation over the joint probability distribution that's described by the Bayesian network, but because of the way that the Bayesian network has split up all these independent terms or conditionally independent terms, we can try to isolate one variable at a time. And we'll do this by looking, in this example, let's look at the C variable first. So these are the terms that depend on the C variable. So let's now have a function. We'll make a function C, or excuse me, f of C, that will take in some W, which is the other variable that this depends on, and outputs the summation of the over C for all these values. And what we gain is, now let's think about what the size of this function is. So this function, it has to be computed by summing over all possible C's, right? So there is some cost here. But that's only 2, or it's K in general. But in this binary, since the C variable in our example is a binary variable, it's just 2 terms that we have to sum over. And then at the end, we end up with a function that has 2 settings, right? It gets W as input, so we can either get a true or a false as input. So we're gonna have to do this twice, but that's not too bad. And then we can, once we have that function, we can rewrite the original probability that we're interested in, or this thing that's proportional to the probability we're interested in, as the following, right? Now we have the same summation of all the terms that didn't depend on C, and then just this f of C function. So we've replaced the summation over C with a function. So let's run through a more general example. So here we have a probability distribution over 4 variables, W, X, Y, and Z. And let's say we're trying to find the probability of Y. Okay, and then the brute force way of writing this, or the full way of writing this, is that you're going to sum over all of the variables that are not in our target probability. So we're going to sum over W, X, and Z. And let's run variable elimination. So the idea is we're going to pick a variable, we're going to eliminate it by replacing it with a function, replacing the terms that affect that variable with a function. Okay, let's do W first. So what are the terms in this summation, or excuse me, in this joint probability distribution that's been factorized? What are the terms that depend on W? So these are the terms, the P of W and the P of X given W. And those are the only terms that depend on W. So from there, we've just now defined a new function that takes in X. And by the way, we have to think about, what should the input to this function be then? And we should look at the terms that are affected by W, so P of W and P of X given W, and think about what are the other variables in these terms. And in this case, the other variables are just X. There's just one variable that's not W. And what we've done by replacing this with this summation over W with a function of X, is that we've eliminated W from the equation, right? So now this is the new equation, and so you can see there's no more summation over W, and there's not even a mention of W. I mean, it's sort of in the subscript, but that's not like that's not the state of W that it has to consider. It's just that it's just an index saying that this used to come from the variable W. So we've eliminated the W variable, and now we can continue. So let's continue. So let's pick the variable X now to eliminate. So what are the terms in this function that depend on X? So here are the terms that depend on X, and we can see that the other variables that are the input to this, or to the input to the functions that depend on x, is just the y variable. So now we have a term that's f of x of y. And then finally, we plug that one back in, and we end up with this. So now we've eliminated the x variable, and we eliminated the w variable before that. Now all we're left with is z, which we can just sum up, and we're done. Right? Then we have computed the probability table for p of y. Right? Not just p of y given an input y, but we can actually we've now actually computed the marginal probability of y. So that was, an example of variable elimination, but where I've sort of just gave you an order to eliminate in, and in general you want to be smart about what order you do, because what order you use for elimination, because it can strongly affect the computational cost of variable elimination. Right? Technically, you can use any order. Right? The math will work when you use any order, but some orders will eliminate large tables quicker, and others will keep them around longer. And a lot of that reasoning comes in by looking at the structure. So let's think about the structure of this Bayesian network. And if you just draw out all the conditional probabilities that I wrote up at the top, you can see that this is a chain structure Bayesian network, right? So there's a W that points to an X, that points to a Y, that points to a Z. So let me summarize variable elimination on one slide. And the idea is that it's based on the idea that every variable that is not an ancestor of a query variable or evidence variable is irrelevant to the query. So let's think about that. So every variable that is not an ancestor of a query variable or evidence variable, and in this case, a query variable is the variable you want to output the probability of, and evidence is something you might want to condition on. So in both cases, those are ones where that's what we want to leave those alone. We don't want to eliminate those. But then everything else should be eliminated. So here's the process. You iteratively do this. You choose some variable to eliminate from the set of non-query and non-evidence variables, and you sum all the terms that are relevant to the variable, and you generate a new factor. And that new factor will take in as input any other variables that are affected by these terms. And then you just keep doing that until there's no more terms to evaluate, no more variables to eliminate, rather. Now, there's no free lunch here. Exact inference with variable elimination in general is sharp p hard, so that's worse than NP hard. But there's certain cases, there's certain types of Bayesian networks for which we can prove that if you use the right variable elimination order, you can get polynomial time, or in even better news, in certain cases we can get linear time. So for a tree-structured Bayesian network, we can get a linear time variable elimination. And we're going to use that specifically in chain-structured Bayesian networks, where we can figure out the order very easily. It's actually we just go in order of a chain, where that means we're going to be able to do variable elimination or exact inference in linear time. So this is one of the foundational methods for inference in a Bayesian network. But now, what about the question of learning? How do you do learning in a Bayesian network? So assume that we have a fully observed situation where we can see, we have a bunch of training examples that tell us the state of every single variable in our distribution. Now, if that's the case, learning is super easy. And we already saw this with naive Bayes, right? It was just counting. Right? Estimate each conditional probability just like we did for naive Bayes. All we do is just count the probability of each variable given its parents from our training set. And then we might add some priors like we did for naive Bayes to prevent overfitting or to prevent situations when we don't have enough data from going crazy. But overall, this is really easy. There's no, it is technically an optimization. We showed this in our derivations, but it's such a simple optimization that you just end up counting and dividing by the number of examples. And that's really good news. And then the slightly less good news is that there's also ways to do this when we don't fully observe everything, and we'll talk about that in the next class or the next video. But of course, you should already have a hint as to how we're going to solve this, because we solved that problem when we have unobserved or latent variables with the Gaussian EM example.